The 601 amps standard ampere rating is primarily used for low-voltage motors and generators found in industrial settings. These include traction motors utilized in electric locomotives, cranes, and various industrial vehicles. It's also common in large generators that support power generation and backup systems and in high-power drives within industrial machinery. Historically, the establishment of standard ampere ratings was closely tied to the current carrying capacity of copper wire, a prevalent material for electrical conductors. The 601 amps rating corresponds to the current carrying capacity of a copper wire with a diameter of approximately 1.5 inches or 38.1 mm. The International Electrotechnical Commission, known as the IEC, has recognized and adopted 601 amps as a standard ampere rating for low-voltage motors and generators. This standardization is important because it promotes compatibility among products manufactured by different companies. While 601 amps holds its place as a standard ampere rating, it's important to note that it is not generally found in residential or commercial electrical applications. These sectors typically operate with lower current ratings, often ranging from 15 to 200 amps. The widespread use of 601 amps in industrial contexts stems from the need to handle high current levels, the reliance on copper wire's capabilities, and the overarching goal of ensuring compatibility across different products through standardization. In the context of electrical engineering, understanding standard ampere ratings is crucial for designing safe and efficient systems. These ratings are not arbitrary. They are rooted in the physical properties of materials, particularly the current carrying capacity of conductors like copper. For instance, the relationship between wire gauge and ampacity is fundamental. Thicker wires can handle higher currents without overheating, which is why larger industrial applications often require conductors capable of carrying hundreds of amps. The National Electrical Code, or NEC, provides tables like NEC Table 310.15b16 that specify the allowable ampacities of insulated conductors based on their size, insulation type, and operating temperature. These tables are essential for ensuring that electrical systems are installed safely and in compliance with regulations. The standardization of ampere ratings, including 601 amps, simplifies the selection of appropriate components for specific applications. It allows engineers to choose motors, generators, circuit breakers, and other devices with confidence, knowing that they will be compatible with the existing electrical infrastructure. Without these standards, the design and installation of electrical systems would be significantly more complex and prone to errors. Furthermore, understanding the historical context of these ratings provides valuable insights into the evolution of electrical engineering. The early reliance on copper wire and its limitations shaped the development of many electrical standards. As new materials and technologies emerged, these standards have been refined and updated, but the fundamental principles remain the same. The IEC role in standardizing ampere ratings internationally is also noteworthy. By adopting common standards, the IEC facilitates global trade and collaboration in the electrical industry. This ensures that products manufactured in one country can be used safely and effectively in another. In summary, the 601 amp standard ampere rating is a specific example of a broader system of standards that govern the design and operation of electrical systems. These standards are based on scientific principles, historical practices, and international agreements. They are essential for ensuring the safety, reliability, and compatibility of electrical equipment and infrastructure. The use of 601 amps highlights the need for high current capacity in specific industrial applications, differentiating it from the low current requirements of residential and commercial settings. Electrical systems are designed to safely and efficiently deliver power to various types of loads. These systems consist of numerous components, including conductors, overcurrent protection devices, transformers, and switchgear. Each of these components must be carefully selected and coordinated to ensure that the system can operate reliably and safely. Conductors are the pathways through which electrical current flows. The size of a conductor is determined by its ampacity, which is the maximum current it can carry without exceeding its temperature rating. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing damage to the system. Transformers are used to step up or step down voltage levels. This is necessary because power is typically generated at a relatively low voltage and then transmitted over long distances at a higher voltage to reduce losses. Transformers are also used to provide different voltage levels for different types of loads. Switchgear is used to control and protect electrical equipment. It typically consists of circuit breakers, switches, and protective relays. Switchgear is used to isolate faulty equipment, prevent overloads, and protect against short circuits. The design of an electrical system involves careful consideration of various factors, including the type of load, the voltage level, the current requirements, and the environmental conditions. Electrical engineers use a variety of tools and techniques to analyze and design electrical systems, including computer simulations, load flow studies, and short circuit calculations. Safety is a paramount concern in the design and operation of electrical systems. Electrical hazards such as electric shock, arc flash, and fire can cause serious injury or death. Electrical systems must be designed and installed in accordance with safety codes and standards to minimize these risks. Regular maintenance and inspection are also essential to ensure the continued safe operation of electrical systems. Electrical standards, such as those developed by the NEC and the IEC, play a crucial role in ensuring the safety and reliability of electrical systems. These standards provide detailed requirements for the design, installation, and operation of electrical equipment and systems. Compliance with these standards is essential for preventing electrical hazards and ensuring the safe and efficient use of electricity. The selection of appropriate electrical components, such as conductors and overcurrent protection devices, is critical for ensuring the safe and reliable operation of electrical systems. These components must be carefully chosen to match the specific requirements of the application. For example, conductors must be sized to carry the expected current without overheating, and overcurrent protection devices must be selected to protect conductors and equipment from overloads and short circuits. Proper grounding is another essential aspect of electrical safety. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to trip overcurrent protection devices and prevent electric shock. Grounding systems must be designed and installed in accordance with applicable codes and standards. Electrical safety training is essential for workers who install, maintain, or operate electrical equipment. This training should cover topics such as electrical hazards, safe work practices, and the use of personal protective equipment. Regular refresher training is also important to ensure that workers stay up to date on the latest safety procedures. The electrical safety audits can help to identify potential hazards and ensure that electrical systems are in compliance with safety codes and standards. These audits should be conducted by qualified professionals who have experience in electrical safety. The 601 amps rating is particularly relevant in industries that rely on heavy machinery and power generation. For example, in the mining industry, large motors are used to power equipment such as crushers, conveyors, and pumps. These motors often require high current ratings, such as 601 amps, to operate efficiently. Similarly, in the manufacturing industry, large generators are used to provide backup power in case of a grid outage. These generators must be capable of delivering high current levels to support critical equipment and processes. The use of 601 amps in these applications reflects the need for robust and reliable electrical systems that can handle demanding loads. The design and installation of these systems require specialized knowledge and expertise. Electrical engineers must carefully consider the specific requirements of the application, the environmental conditions, and the applicable safety codes and standards. Regular maintenance and inspection are also essential to ensure the continued safe and reliable operation of these systems. The 601 amp standard ampere rating is just one example of the many standards that govern the design and operation of electrical systems. These standards are constantly evolving to reflect new technologies and best practices. Staying up to date on the latest standards is essential for electrical engineers and other professionals who work in the electrical industry. The development of electrical standards is a collaborative process that involves input from industry experts, government agencies, and other stakeholders. This ensures that the standards are based on sound scientific principles and reflect the needs of the industry. The use of 601 amps and other standard ampere ratings helps to ensure the safety, reliability, and compatibility of electrical equipment and systems around the world. These standards are essential for supporting the global economy and improving the quality of life for people everywhere. In the realm of electrical engineering, the concept of impedance plays a crucial role in understanding how electrical circuits behave, especially when dealing with alternating current or AC. Impedance, denoted by the symbol Z, is the total opposition that a circuit presents to the flow of AC current. It's a more comprehensive measure than resistance alone, as it includes both resistance, which opposes current flow in both AC and direct current, or DC, circuits, and reactance, which is the opposition to current flow due to capacitance and inductance in AC circuits. The unit of impedance is the ohm, just like resistance. Impedance is a complex quantity, meaning it has both a magnitude and a phase angle. The magnitude of impedance represents the total opposition to current flow, while the phase angle represents the phase difference between the voltage and current in the circuit. This phase difference is a key characteristic of AC circuits and is not present in DC circuits. Reactance, the component of impedance that arises from capacitance and inductance, is frequency dependent. Capacitive reactance, denoted by Xc, decreases as the frequency of the AC signal increases. This is because capacitors store energy in an electric field, and at higher frequencies, they can charge and discharge more quickly, allowing more current to flow. Inductive reactance, denoted by XL, increases as the frequency of the AC signal increases. This is because inductors store energy in a magnetic field, and at higher frequencies, they resist changes in current more strongly. The total impedance of a circuit can be calculated using the following formula: Z equals square root R2 plus XL XC2, where R is the resistance, XL is the inductive reactance, and XC is the capacitive reactance. This formula shows how resistance and reactance combine to determine the overall opposition to current flow in an AC circuit. Understanding impedance is crucial for designing and analyzing AC circuits. It affects the amount of current that flows in a circuit, the voltage drops across different components, and the power dissipated in the circuit. Impedance matching is a technique used to maximize the power transfer between two circuits. This is achieved by ensuring that the impedance of the source circuit is equal to the conjugate of the impedance of the load circuit. Impedance matching is important in various applications such as audio amplifiers, radio transmitters, and telecommunication systems. In summary, impedance is a fundamental concept in electrical engineering that describes the total opposition to current flow in AC circuits. It includes both resistance and reactance, and its value depends on the frequency of the AC signal. Understanding impedance is essential for designing and analyzing AC circuits and for achieving optimal power transfer between circuits. The 601 amps rating, while seemingly a specific value, fits into this broader understanding of electrical circuit behavior and the need to manage current flow effectively within defined impedance parameters.